Okay, so this is a real pain. The battery went dead on my recorder, so I'm going to have to do a voiceover for this solution. So we are looking at the three equations that we want to take from your formula sheet. So the first moment of area, and then we're going to use this equation here. We'll use this for nails. Strictly speaking, this shouldn't really be used for nails, but we'll use that. Notice the H is referring to the shear force that you're going to go for the nail. The V is referring to the shear that you get from when you do your shear force diagrams. So you put a bit of, we've got a beam there, applying some weight, and we're going to end up with a shear force diagram there. What about this delta term? Okay, sorry, I'm talking about the Q term here. So the Q is your first moment of area, and that can be either, you can work that out in terms of the blue section or the gold section. Basically, I'm looking at where am I going to divide my well, rather, where's it going to shear? So that's what I'm saying to myself. So, and then I sort of say, well, I've got two possible sections there. So I could either have this gold section and say that's shearing away from the blue, or I could say that the blue section is shearing away from the gold. So you can choose either, and you'll end up with the same result. Now, obviously, the thing you want to choose is the simpler shape. So in this case, we'll choose the blue. The YC is defined as the distance away from the neutral axis, and you know what the neutral axis is for this particular problem. It's straightforward. It's going to be straight in the middle. And you notice that, as I said, doesn't really matter which section you would choose, you would end up with the same result, because in this particular case the YC is straight in the middle. So that middle section there is going to give me A times 0. Now this delta x term is not really supposed to be what this equation is used for, but we're going to say that that delta x represents the spacing between each section. And the H we're going to say is the shear force allowed for now. If you've got more than one nail, you can then double that number. Let's say you've got two nails being sheared through, in which case you can double your shear force that you can take. The I, you can see there, is going to be the second moment of area for the complete section. Now this particular question here, they're asking us to find the allowable shear. So they're asking us, this is a bit unusual, to actually find the V. Normally we would be asked to find what the H is, probably. You'd probably want to work out what kind of shear force that your H would be. But this particular question is asking us to find the V. So let's write out what we know. We know what the H is, so we can shear through. Notice I'm just shearing through one nail. I've ignored the other nail. So I can shear through one nail, and that's with 400 newtons. The Q I can work out, well, I'm going to base it on my top section. So it's got a width of 120 millimeters. It's got a depth of 60, so that's my area done. And the distance, so we're looking for the distance from the neutral axis to the centroid of that particular section that we're trying to shear, and that's going to be 60 again. Stick that into my calculator, and we will then convert that so that it's going to be in meters to the power of 3. So divide by 1000, divide by 1000, divide by 1000, and we get that number. Let's press the SD button, and we're going to get 3.4.32 times 10 to the minus 4 meters to the power 3. Next, we'll use this term here, so we're using that to represent the spacing. And we can see the spacing between the nails is 75 millimeters. Convert that to meters, you're going to end up with 0.075 meters. Finally, I want to find my I, so that's going to be summing up all my 12ths BDs to the power 3, all square or rectangle sections, plus the parallel axis component, so that's the AH squareds. Your H in this case is actually going to be the same as your Y, curiously. So if we was dealing with more complex shape, that wouldn't be necessarily the case. But here we've got looking for the H, and so we're looking for the distance from the neutral axis to the particular sections that we're dealing with. So we're not just dealing with the section we're trying to shear away. We've also going to have potentially AH squared for the middle section. Now, since the middle section is bang in the middle, we end up with H equals 0. So let's start summing up our 12ths BDs to the power 3. Well, I use the fact that we've got symmetry there, so I'm going to say that we've got 2 12ths there. So 2 12ths, the width there is 120 times 60 to the power 3, and then the middle section we've got 1 of them, so 1/12, 200 times 60 to the power 3, so that's the 12ths BD to the power 3. So notice I've used symmetry there, and I've doubled the top and bottom one. Now for my AHs, well, I can see that I'm not going to get any AH squareds for the middle section, but I will get them for the top and bottom sections. So the areas for them, top and bottom, is 120 times 60, got 2 of them, and the H, the distance away from the neutral axis to the top, is 60, so make sure I square that, so 60 squared. Let's stick all of that into my calculator, and what am I going to get? Okay, so let's convert that answers. I've worked everything out in millimeters. This time, remember that second moment of area, that's in meters to the power 4. So you want to divide by 1000, and again, and again, and again, so 4 times. So that gives you 1 times 10 to the 12. So that's in nice SI units, in meters to the power 4. Let's take our equation now. So this particular question is asking us to work out the the allowable shear. So the allowable shear force there. So rearrange the V. So we've got high divided by QS. S is actually the symbol that you would more traditionally use for when you're doing a Nell problem. So just plug our numbers in there. We see that we've got 738 newtons. Notice that's a force, so we've got a solution that we can use.